Picture a classic movie scene. You know, the kind where someone is just being tickled mercilessly on the living room floor. Or maybe imagine a scene of kids just roughhousing, tumbling around, and wrestling in the backyard. Picture the sound of their laughter.
Yeah, it's immediate, right, and incredibly visceral. Like you hear that sound and you almost feel the reverberation in your own chest. It's this highly contagious biological reflex.
Exactly. And no matter who is laughing or, what movie you're watching or even what language the people speak, it always has this universal cyclical rhythm, that almost uncontrollable ha 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 sound.
Right, it's an experience shared by literally every human being on the planet.
But here is a really strange question to consider. Why does that specific ha 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 rhythm happen? And maybe more importantly, where did it actually come from?
That is the million-dollar
It
question.
really is. So welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research from advanced biomedical technologies to breakthroughs in evolutionary biology, all told as compelling, easy-to-follow stories for you.
And this is really the perfect topic for us to explore today, because laughter is one of those everyday behaviors that we just completely take for granted.
Oh, absolutely.
I mean, we laugh, we breathe, we sleep, we don't give it a second thought. But when you actually put laughter under a microscopic lens, you find that it contains this incredibly deep evolutionary history. It's like it's an ancient artifact hiding in plain sight.
Which brings us to the core mystery for today's deep dive, because scientists who were looking for the origins of human language didn't actually start by looking at words or, ancient texts or even the shapes of our mouths.
No, they didn't. They looked at our closest evolutionary cousins during playtime.
Yeah, and they uncovered a secret rhythm hidden right there in our giggles. But before we get into the actual discovery, we need to understand why scientists were looking at giggling apes in the first place.
All right, so to understand the origin of this investigation, we have to look at the fundamental hurdle in evolutionary biology. When you're trying to figure out how humans learn to speak and how we develop the vocal control to form complex words and sentences, you hit a massive wall.
A physical wall.
Exactly. And that wall is simple physics. Sound does not fossilize.
Man, that sounds utterly maddening for a researcher. We have ancient bones, right? We have stone tools. We have fossilized footprints baked into the mud.
We do. We can literally see how our ancestors walked.
Right, and we can analyze their teeth to see what they ate, but we cannot dig up the vocal origins of human song or speech. You can't just, put a prehistoric conversation in a museum display case.
Which means researchers are forced to look for living proxies. They have to study the extant or currently living models of our ancient past.
Okay.
And in this context, that means looking at the non-human great apes, so orangutans, gorillas, bonobos, and chimpanzees.
Got it. And for a long time, the scientific community has known that laughter is conserved across all of these great apes, right? It's a shared biological trait.
Yes, exactly. And they'd use it in a very specific way. Across all these species, including humans, laughter happens primarily during affiliative interactions.
Like social play.
Right, like playing. It's an evolutionary tool to signal benign intent. It basically tells the rest of the group, hey, we're just playing. No one is actually getting hurt here. Stand down.
That's a brilliant mechanism for maintaining social coordination. But it sounds a bit like trying to figure out the evolution of modern jazz by only looking at modern bands, because all the ancient sheet music and early instruments burned in a fire. Modern humans can improvise and make all these complex sounds, and, apes make basic sounds, but the bridge between the two is just missing.
That is a perfect analogy. The bridge is completely invisible.
But I have to push back here a little bit. Laughter is chaotic, it's messy, it's literally an involuntary spasm. How can measuring a few ha-has today prove anything about a hominid from 15 million years ago? That feels like a massive leap.
Well, it's a totally valid skepticism, and it forces us to ask how you can possibly measure something as fleeting as a laugh to prove an evolutionary timeline. And the answer the researchers came up with was to stop analyzing the sound itself.
Wait, really? Stop analyzing the sound?
Yeah, ignore the pitch or the tone. Instead, they started looking strictly at the temporal structure. They wanted to analyze the exact timing and the rhythm of the laughter sequences.
Oh, I see. Because laughter, at its core, is inherently repetitive. It's cyclic. It's a series of bursts. Ha, ha, ha.
Precisely. And if you can measure the differences in the timing, the regularity, and the flexibility of those sequences across different species, you might just find a window into how respiratory and vocal coordination evolved across the branches of the hominid family tree.
Okay, wow. So how did scientists actually pull this off? Because designing a test for this sounds like an absolute nightmare.
It was definitely a challenge, but a really clever team of researchers recently tackled this very problem. The findings were published in the Nature Portfolio Journal Communications Biology in June 2026.
Right.
The research was led by Dr. Chiara Di Gregorio, Marina Davila Ross, and Adriano R. Lamera, representing the University of Warwick and the University of Portsmouth.
And the data set they managed to compile is really what makes this so special. They gathered rare audio recordings of 17 young subjects, ranging in age from 6 months to 7 years old.
It's a fantastic data set.
Yeah, the breakdown was 4 orangutans, 2 gorillas, 3 bonobos, 4 chimpanzees, and 4 human children.
And getting high-quality recordings of young, non-human great apes is incredibly difficult. I mean, they're rare in captive populations, and you can't exactly just instruct them to perform for a microphone.
Hey, buddy, laugh into this mic for me.
Yeah,
Not gonna happen.
exactly. So this data set is deeply precious to the scientific community. By looking at these 4 specific ape species alongside humans, the researchers were essentially looking at different branches of our shared evolutionary tree, allowing them to triangulate backward in time.
Okay, so they ultimately recorded 140 laughter bouts. But they didn't just record them randomly throughout the day, right? They recorded them during 2 very specific controlled contexts.
Right, social rough-and-tumble play and tickling.
And the methodology they used to analyze these tapes is where the science gets really intense. Because they couldn't just listen to the tapes and tap their feet to the beat.
No, the human ear is simply not precise enough for this kind of work. The precision required audio engineering at a microscopic level.
Yeah, to measure the fraction of a second intervals between each individual haw in a single laugh,
Yeah.
they needed the audio to be pristine. They resampled all the audio files to 22,050 hertz.
Which is incredibly detailed.
Yeah. To put that in perspective, that means their software was taking over 22,000 individual snapshots of the sound wave every single second. It allows you to see the exact millisecond a sound begins.
And then they applied a 60 hertz high-pass filter.
Which is crucial, right? Because when you're recording in an animal enclosure or a living room, there's always background noise.
Exactly. That 60 hertz filter strips out the low electrical hum of power lines or heavy machinery, leaving only the pure biological sound of the laughter.
Okay, so they have these incredibly detailed, crystal clear digital waveforms on their screens. What exactly were they measuring?
They defined a call as a continuous sound element without a gap. Then they measured what is called the inter-onset interval.
The inter-onset interval.
Right. In plain terms, that's just the exact duration from the very start of one sound to the very start of the next one. This measurement served as their proxy for the tempo of the laughter.
Oh, clever.
Yeah, they mapped out the tempo of all 140 laughter bouts across all the species.
Yeah.
And when they ran all this data through their statistical models, they found their first major breakthrough.
And this is where the story takes a really fascinating turn.
The data clearly revealed that great ape laughter is isochronous.
Wait, let me stop you there. Isochronous, does that mean it operates literally like a metronome? Like they are laughing on a perfect mathematical beat?
Almost exactly like a metronome. Isochrony means the timing between each vocal burst is highly regular and equally spaced.
Wow.
Yeah, when an orangutan or a chimpanzee laughs, the gap between the first ha and the second ha is practically identical to the gap between the second and the third. It is a steady, predictable rhythm.
That's wild.
And because this specific rhythmic trait is shared across orangutans, gorillas, bonobos, and chimpanzees,
That means our last common ancestor, who was living roughly 15 million years ago, was already laughing with a rhythm that we would instantly recognize today.
exactly.
15 million years ago. Long before fire, long before language, the hominid family was already going ha-ha-ha on a mathematically steady beat.
It really is a remarkable realization. It establishes a firm evolutionary baseline. We know what the starting point was, but then the researchers took the next step.
Okay.
They separated the data by the context of the laughter. Remember, they recorded the subjects during rough and tumble play and during tickling. And this is where the study introduces a brilliant twist.
Oh, I love a twist.
The isochrony, that perfect, regular rhythm, was highly dependent on what the subject was actually doing with their body.
Right, so the tickling laughter was highly regular. When the apes were being tickled, they kept that perfect, steady metronome beat. But the laughter during rough and tumble play deviated significantly. It became chaotic. It wasn't strictly regular at all.
Which forces us to ask why. Why would the rhythm break down during play, but stay perfect during a tickle session?
Good question.
The answer comes down to the deep mechanics of physiology and the respiratory system.
Because social play is dynamic. It involves wrestling, torsion, tension, thumping, and compressing of the chest cavity.
Exactly. Think about the physical mechanics of breathing. Your diaphragm pulls down, your lungs expand, oxygen rushes in. When you vocalize, your lungs push the air back out through your vocal cords.
Right.
Well, during rough and tumble play, that physical act of wrestling violently disrupts the respiratory cycle. A sudden thump to the chest forces air out unexpectedly. Twisting your torso restricts how far the lungs can expand. The diaphragm is literally being bumped and jostled around.
It's like trying to sing a perfectly steady, beautiful note while someone is forcing you to do burpees.
Exactly.
Your breath is just going to hitch. Your vocal output is going to be interrupted by the heavy, unpredictable physical demands being placed on your lungs.
That is a highly accurate way to visualize it. The physical chaos of wrestling creates vocal chaos. But this realization is what makes the tickling data so incredibly important.
Because rough play disrupts the breath.
Right, so the researchers realized that tickling provides something totally valuable. A stable, unaltered window into the pure underlying rhythm of the nervous system.
Because when you're being tickled, you're relatively stationary. I mean, you might be squirming, but you aren't doing heavy aerobic wrestling. You aren't experiencing heavy impacts to your thorax.
Precisely. The vocal rhythm you hear during tickling is the true baseline evolutionary rhythm. It's the pure signal of the respiratory vocal connection, entirely free from the mechanical noise of a physical wrestling match.
Okay, so the researchers have isolated this pure signal. They know ape laughter is fundamentally rhythmic and tied directly to their breathing. But what did this massive data set show them about human beings? Because we were in the study too, right?
We were.
The human kids were being tickled and playing right alongside the apes, so did we keep the metronome?
Well, this is where we see the ultimate human deviation. The researchers used phylogenetically informed statistical analyses.
Which means?
It just means they looked at how these laughter traits shifted along the branching timeline of our family tree, moving from the oldest lineages to the modern ones. And the timeline showed a clear, gradual trend. Over 15 million years of hominid evolution, the baseline tempo of laughter accelerated.
Humans today laugh faster than our ancient ancestors did.
We do. But more importantly, only humans broke the evolutionary mold when it came to context.
Yeah, this was the finding that completely hooked me. Only humans subconsciously changed the speed of their laughter based on the context. The great apes did not do this.
No, they didn't.
An ape's pure baseline rhythm is the exact same, whether you were tickling a chimpanzee or an orangutan. But the human children laughed faster during tickling than they did during play. They modulated their tempo.
Furthermore, humans exhibited the highest temporal variability overall. Our laughter is the least rigid, the least purely isochronous of all the species tested. We have an incredibly high rhythmic range.
Okay, I have to pause here and ask you to explain why this matters, because on the surface, this feels counterintuitive.
How so?
Well, if you told me my rhythm was variable, chaotic, and inconsistent, I'd assume I was failing a music class. Why is being inconsistent or variable in our laughter speed considered an evolutionary upgrade? Shouldn't perfect rhythm, perfect isochrony be the ultimate goal of a highly evolved vocal system?
It's an excellent question, and the answer is fundamental to understanding human evolution. In the context of evolutionary biology, variability equals plasticity, and plasticity equals control.
Plasticity, the ability to stretch, adapt, and change a behavior on the fly rather than being locked into a reflex.
Yes. Think about how a great ape produces a sound. Their vocalization is deeply, intrinsically tied to their biological respiratory cycle. They breathe in, they breathe out, and the sound is locked to that mandatory mechanical rhythm. It's on autopilot.
Oh, I see.
But human speech requires us to completely override our basic breathing patterns. Consider what you're doing when you're talking to me right now.
Well, I'm holding my breath. I'm releasing it in tiny, controlled bursts. I'm pausing, shaping vowels with my mouth, and modulating the airflow completely independent of my body's basic need for oxygen.
Exactly. You are uncoupling your voice from your lungs' natural biological autopilot. That progressive loosening of the coupling between vocal output and the strict respiratory cycle is the exact mechanical freedom that allowed humans to develop speech.
Wow.
Yeah, the fact that human laughter is highly variable, that we can speed it up or slow it down based on whether we are being tickled or wrestling, shows that we have broken the strict biological lock that keeps ape laughter so perfectly, rigidly rhythmic.
That makes so much sense because if you think about it, a rigid, perfectly timed laugh actually sounds incredibly unnatural to us today. If I walked up to you and laughed with perfect millisecond precise isochrony H-A, it wouldn't sound joyful.
No, not at
It
all.
would sound robotic. It would sound creepy.
It absolutely would sound creepy. And that perception is deeply wired into our social brains. For humans, variable timing in laughter is perceived as emotionally positive. It conveys complex social intent.
Right.
When your laughter speeds up unpredictably or when the rhythm shifts and cascades, it amplifies positive emotional contagion in the room. It tells the people around you that you're highly engaged, that you're experiencing complex joy rather than just firing off a stereotyped involuntary biological reflex.
So we use the chaos in our laughter to communicate nuance. Like a slow chuckle means something completely different than a fast, breathless giggle, and we use those variations to navigate our social worlds.
Exactly. The rhythmic functional span of human laughter conveys our emotional state, our intent, and our disposition. And what the Warwick and Portsmouth researchers found was that this temporal variability decreased the further back down the phylogenetic tree they looked.
Showing that progression over time.
Right, which reflects a beautiful, gradual evolutionary trend in vocal flexibility across our hominid family tree.
So the ability to speak wasn't a lightning strike at all. This discovery proves that human vocal plasticity didn't just appear overnight. It falls on a direct, measurable continuum.
Exactly.
Our ability to speak, to sing, to debate, to modulate our voices, all of it stems from a gradual evolutionary loosening of our breathing and vocal rhythms over 15 million years. And you
Yeah.
can still measure that ancient history today just by recording how a toddler giggles when you tickle them on the living room floor.
It transforms laughter from a simple social signal into a living, breathing model of our deep evolutionary past. Because we can't dig up a fossilized voice, laughter serves as an accessible, living fossil of our communication.
That reframes the entire concept of human noise.
Right.
Let's bring this all together for you, the listener, because we have covered a massive amount of ground today spanning millions of years of history.
We certainly have.
First, that rhythmic, universal ha-ha-ha of laughter is a 15-million-year-old inheritance. It is a baseline rhythm shared with all extant great apes, connecting us directly to our oldest common ancestors.
Second, we learned that the mechanical physical differences between rough play and tickling were the key to isolating this ancient rhythm. By looking at the relatively stationary act of tickling, scientists could strip away the respiratory disruption of wrestling and isolate the pure evolutionary vocal rhythms tied to the nervous system.
And finally, the most important takeaway. The chaotic, variable speed of human laughter isn't a lack of rhythm. It's a sign of immense evolutionary plasticity. It represents the advanced, decoupled vocal control that allowed our ancestors to break free from rigid biological breathing cycles, which ultimately gave us the physical mechanics required for language and speech.
Which leaves us with a fascinating perspective to consider moving forward. If the fundamental blueprint for human speech and language was hiding all along in the involuntary rhythm of a belly laugh, what other ancient evolutionary secrets are coded into the everyday noises we make?
Oh, wow.
Right? What could a gasp, a sigh, or an involuntary cry reveal about the millions of years of history living inside your own throat?
I don't think I will ever hear a laugh the same way again. It is incredible to think that every time we giggle, we are echoing millions of years of evolution. Thank you so much for joining us on this investigation here on Deep Dive Lab. We warmly invite you to follow and subscribe for more incredible journeys into the science hiding in plain sight. Keep wondering, keep listening, and we will catch you next time.